It's my honor to be here and have the presentation. And I'm MENG from Department of MSE, and my supervisor is Professor Johnny Ho. Today I will talk about the nanostructure perovskite and their device application. And it's the outline. At the beginning, I will introduce the research motivation of the nanostructure perovskite. And after that, I will show some research works about advanced optoelectronic device with perovskite nanowire. And at last, it's a brief summary and acknowledgement. So, with the development of modern electronics, the component devices are becoming more powerful but smaller. The semiconductor with nanoscale size has becoming the building blocks for the nowadays information technology. For example, using in camera, in display, and in computer. And with the continuous downscaling of field effect transistor, their structure changed from planar MOSFET to 3D FinFET to gate-all-around nanowire activity, and their corresponding device size decreasing from 10 nanometer to 0 nanometer. And from this cross-section TM, we can see the nanowire have a very small diameter, about 8 nanometer. And it's very special one-dimensional carrier transport. And also, it's all around nanowire structure. So nanowire may be a good choice for future electronics. And the semiconductor nanowire have many advantages in terms of carrier transport, the energy efficiency, the mechanical flexibility, and the optical symmetry, and also more importantly, the device with a small size. And in addition to the electronics, the nanowire can also be used in many different kind of optoelectronics applications. The semiconductor nanowire have band gap and the corresponding wavelengths having the UV light, the visible light, the near infrared, the SWIR, the NIR light. And as a result, you can use in imaging, the communication, the night vision, and different kind of spectroscopy. For achieving high nanowire quality and with controllable synthesis, the chemical vapor deposition method, CVD method, are generally used to fabricate the nanowire. And aftergrowth, for achieving large area device integration, the contact plating method could be used to achieve the parallel nanowire array for large area device application. And as for the device application, the nanowire can be used in different kind of electronic and optoelectronics. For example, the high mobility field effect transistor by using indium arsenide barrier nanowire, and also the flexible solar cell based on gallium arsenide nanowire, and the high performance photodetector use the photo gating nanowire, and also the artificial visual system and other neuromorphic device, and can also be using light imaging diode use nano engineering method. As for perovskite nanostructure, actually back to 1999, the first perovskite thin film transistor was reported. It had a whole mobility about 0.6 centimeter square per watt per second. And this work showed the potential high mobility in halide perovskite, which is mainly because of the very small carrier effective mass. But the film in this work is spin coated with crystal structure. If we can make it into single crystal nanostructure, we may get high material property and a high device performance. And in addition to the performance enhancement, we can also study the material property of perovskite nanostructure and perovskite nanowire. For example, we can study the thickness-dependent property. For example, the quantum confinement effect. And we can also use the surface state to modify the device performance. And also we can study their composition, their structure, and their application diversity for the perovskite nanostructure. And the next session, I will show the advanced electrode device use perovskite nanowire. Actually, there are several kind of methods to help the vapor deposition of perovskite nanowire. The left image shows the epitaxial growth of cesium-lead bromine-3 nanowire on mica substrate. And the middle image shows the nano-engineering template method by using a CVD system. But these methods have drawbacks and difficulty. For example, specific substrate like mica is needed, and high temperature is required. And because their growth features, it's challenging to fabricate multi-terminal device, and also it's difficulty to construct the heterogeneous structure for functional device. Different to this method, VLS may be a better choice. What is the VLS growth? This picture shows the brief growth mechanism. The vapor source comes into the liquid catalyst seed, and after oversaturation, the solid product is got. Because of the VLS growth features, the VLS has some advantage. For example, it's controllable, and as a result, we can get high quality products of nanowire, and also no substrate requirement is needed. So we can use some amorphous silicon oxide as the substrate, and also the growth temperature is low. So the VLS growth is an effective route to achieve high quality nanowire. And how to realize the VLS synthesis of cesium-lead halide-3 nanowire? First of all, the T nanoparticle was drop casted on silicon oxide, and then a CVD system was used to produce the nanowire. And from the SEM shown here, we can see the vertical growth of cesium-lead halide-3 nanowire out of the substrate. And from the EDS mapping shown here, we can see the cesium, lead, and bromine uniform distribute over the nanowire. But at the nanowire tip, it's mainly composed of the lead and T. So it's the direct evidence of VLS growth. And here is a TM image. The nanowire has a diameter about 130 nanometer, and it's close to the diameter of T nanoparticle used in this work. And from the high resolution TM, we can see the continuous lattice across the nanowire body. So we can see the nanowire is single crystal. And from SAAED and the atomic TM, the crystal structure of nanowire is cubic. And all the nanowire used in this method is grow along the 100 orientation. And we also do the SRD measurements on 3 different kinds of nanowire. And all the flash peaks are indexed to the perovskite phase. And we also check the optical property. All 3 kinds of nanowire show single emission peaks and cover the entire visible light region. After the successful fabrication of cesium-lead halide-3 nanowire, we also made the transistor based on this nanowire. A bottom gate top contact device structure is used. The cesium-lead RS3 nanowire was used as channel. And the 270 nanometer silicon oxide were used as gate dielectric. And 8 nanometer gold were used as source and drain electrode. And here is the SEM image of the device. And as a result, the transistor based on the cesium-lead RS3 nanowire show Hall mobility up to 3.05 centimeter square per watt per second, and it's higher than other inorganic fluorescent device. And from the transfer curve, we also can see the typical P-type conduction behavior, and it's mainly because of the accept-like surface state and the self-doping process related to tin impurity dopings. And in next work, to avoid the tin impurity dopings, we use gold catalyst to gloss the fluorescent nanowire. As we all know, the gold has a high melting temperature about 1000 degrees Celsius. But we found in a exothermic reaction, the gold lead alloy is formed with a low melting temperature about 212 degrees Celsius. Such kind of low temperature is beneficial to the VLS growth of cesium-lead iodide-3 nanowire. And below is the EDS mapping. We can see the cesium-lead and iodide-3 uniform distributed on the nanowire. And the nanotip is mainly composed of gold and lead. It's a kind of VLS growth, and it's also similar to the tin-seeded growth. We also made the photo detector based on two kinds of nanowire, and we can see the gold-seeded nanowire show lower dark current and a high detectivity up to 10 to the power 14 joules. And also, it shows the reliable operation with time. And in the response curve, we can see the gold-seeded device has a fast response speed, about 120 microseconds. This is faster than the tin-seeded nanowire. The tin-seeded nanowire has a response time about 240 microseconds. We also compare the detectivity, responsivity, and the response time with other reported results. The photo detector based on the gold-seeded cesium-lead iodide-3 nanowire show better performance than most inorganic fluorescent photo detector. Next session, to further improve the mobility, we use surface doping method to improve its mobility and stability of fluorescent nanowire. Molybdenum oxide were used as surface doping in this work because it has a very high work function, about 6.8 EV. It's significantly larger than the cesium-lead bromide-3 nanowire. If the cesium-lead bromide-3 contacts with the MO3, the electron will move from the fluorescent to the oxide. And as a result, there will be a hole-rich layer at the cesium-lead bromide-3 surface. This will be beneficial for the carrier transport. And from the HRTM, we can see the amorphous MO3 layer, uniform cover on the cubic cesium-lead bromide-3 nanowire. And we can also see a very sharp interface between the MO3 and the cesium-lead bromide-3. And from the UPS, we can see the work function increasing with the MO3 thickness from 4.8 to 5.9 eV. This is a direct evidence for the surface doping of MO3 on cesium-lead bromide 3 nanowire. And this is also agree well with the XPS spectrum. After the successful fabrication of crucial nanowire, we also made a transistor based on this kind of crucial nanowire. With the increasing thickness of MO3 from 0 to 10 nanometer, the mobility increasing from 1.5 centimeter square per watt per second to 23.3 centimeter per watt per second. We also measure their photo detection performance. The photo current increased from 5 nanoampere to 14 nanoampere. In addition to the mobility enhancement and photocurrent enhancement, from the MO3 can also provide the surface passivation function on cesium-lead bromide 3 nanowire. And from the transfer curve, we can see the crucial nanowire can maintain 18% of their initial mobility. In contrast, the pristine cesium-lead bromide 3 shows severe performance deterioration. We also use SEM to check the morphology evolution of nanowire with time. The crucial nanowire can keep the structural integrity even storing them into ambient for 30 days. But at the same condition, the pristine cesium-lead bromide 3 nanowire shows severe morphological deterioration. And we also studied the PL mapping of this nanowire. The crucial nanowire can show the complete and uniform PL signal across the entire nanowire. But in contrast, in the pristine nanowire, they are losing PL signal with time. The PL mapping result is agree well with the SEM image, and also highlighting the surface passivation function of MO3 on cesium-lead bromide 3 nanowire. In summary, for the first time, we introduced the VRS synthesis to the cesium-lead halide 3 nanowire. And after that, high performance transistor and the photodetector is built, and some performance parameter are recorded high. And to avoid the tin-related impurity dopings, we use gold catalyst to take place of tin. And as a result, we can get the lower dark current and high detectivity. And also we use the surface doping method to improve the mobility and the stability of perovskite crucial nanowire. Overall, the synthesis method, the device structure, and the operation concept are useful for future nanostructure perovskite and their device applications. Thanks for the support from my father, Professor Johnny Ho, and all my group members. And thanks for the invitation from HKRCE. That's all my presentation. Thank you.